First, let me thank the conference organizers for inviting me, and probably more for running this conference in this unusual time. I attended many sessions, quite a few talks yesterday, and I enjoyed them a lot. And I feel running a remote conference like this, put some normality back into our lives in this uncertain time. And it's just really nice to listen to some technical talks. So let me just directly go into what I'm going to talk about today. It's how to use neural networks in some physical layer communication problems. And let me start with, I have a number of collaborators on this line of work, because I'm going to explain quite a few different things. And let me quickly go through them. Shaolun is my former student teaching in Tsinghua University now. Xiang is his student. My student Anuran, David, both just graduated. Mohammed is still going on. This is my colleague Greg Winnell, and my colleague Lingjia Liu in Virginia Tech, who just got the Best Paper Award. And Jojo is his student. Yeah, so this is a pretty long list of collaborators. Let me start. So deep learning, everybody know it's a very successful, very exciting direction. And it's actually developed into a rather mature stage. This is one picture I stole from the internet. This is a model of what's called Inception. It's a common solution for ImageNet, image recognition network. It's actually really complicated. Each of this block would expand into a block like this, and a block would be 10 blocks like that. So it's a rather difficult deep neural network with very commonly tens or hundreds of thousands of parameters in it. And it can be used to achieve rather sophisticated problems. And even in the deep learning people, that community, people are also, rather after they got surprised by how well they can do. And now the question is always, where do we find the next step? If you think of the current success in computer vision and natural language processing, they're all rather complex problems, but with not much of a clear mathematical model. This is quite distinctive. How do we model people's speech, right? There is not really a very good mathematical model of that, or at least not a simple one that is tractable. And beyond these a few rather special applications, the idea is if we would like to have bigger impact of deep learning, these type of super computation power, then the next step is probably to use it in other interdisciplinary fashion in other areas like energy, like economics, like communication, right? And well, this is where we believe the next step is in. Well, there's a big difference between those problems, and what we have already as a success is that there in most of the other disciplines, they're engineering disciplines. They have a lot of human design in it, and those problems, we have structures, we have models, we have physical laws, constraints as equations, and so basically we have a lot of domain knowledge. And no matter in which area, if you study for long enough, you should draw the conclusion that without this knowledge, you can't work in this area. And now if you go back to see a big neural network, it become clear that in a network like this complicated, suppose you would like to have some kind of a model or prior knowledge you want to put in. It's not clear where you can put those knowledge in what form into a network. So the marriage between deep learning and other engineering disciplines with domain knowledge has been difficult. And another difficulty of using neural network is this is much of that is empirical performance based. So you know, for example, in COM, we have very clear performance benchmark, and not only that, we need guarantees, you know, reliability, optimality, and we need robustness, and we need our system to work in all areas, in all scenarios. Yeah, doesn't quite have that kind of guarantee with deep learning, so that's an issue. Right, so that's the communication problem is probably one of the best example to apply machine learning into engineering discipline, because you know we are the I like to believe that we are the best developed engineering discipline. We have very clear set of mathematical rules. And some people would believe that next 6G, the revolution come from some using of machine learning. Well, it's not clear. Like yesterday, Tom Mazada mentioned, not clear, right? But we would hope that can be a step forward. And the reason machine learning is such good, powerful tool is not clear it's gonna make such a big impact is because of the following difficulties. It usually requires too much resource. You know, you can't put a GPU on your cell phone, right? The competition is too much, and probably harder than that is, I hear a few talks yesterday talk about the sample complexity. In communication, we train a channel with, you know, just a few training samples, and in machine learning, hundreds of thousands or tens of thousands samples, it's very common. And no guarantee, I mentioned that. And reusable solution, domain knowledge. In COM, our solution is never designed for a single scenario. There are always parameters into your receiver or whatever solution you have. For example, SNR is a parameter. We would like to come up with a receiver that works on all SNR, and then we can tune the SNR to change the solution, and at every SNR of a receiver is the optimal. This kind of parameter tuning, reusable solution from one scenario to a different scenario, that is hard in deep learning. And I like to also mention this, that because of these problems are engineering designed, it's human design, it's not clear whether they can work with, for example, this SGDs, stochastic gradient descent. You know, some problems could be that our design precisely made SGD very hard. One example of that is the decoding problem. It's making this gradient descent really, really difficult. So the bottom line is there are some really different mindset between the neural network and communication, you know, our COM designs. I like to, from here, quote Bob Gallagher. When Bob talked about, you know, how we communication engineers work, this is his quote. He said that it's human nature to prefer simplicity. What he meant by saying this is that communication has a methodology to start from bottom up. So we always work on the simplest model first, develop our intuition, insights, and entire theory, and then build on that. We start with a binary symmetric channel, Gaussian channel, and build up to handle very complicated communication systems. And if you think of this, it's really different from what neural network approach, where there's nothing simple about that picture I show you on a neural network. It's very complicated. It's a overall solution, empirical performance driven. It's data driven. In contrast to what we have is what I would call model driven, more analytical approach. The question is not which approach is better or correct. That's the wrong question to ask. The question is, how do we put the two together, right? Because each method has some advantage of its own, and the question is, how do we put them together? Oh, in this talk, I'm going to do two things. I'm going to briefly give a information theoretic interpretation of learning in neural networks. I need to do that because this helps you to make the connection between this complicated neural network with some basic language we like to use in signal processing in COM. And but I have to do this very briefly because number one, doesn't, you know, this topic itself take very long, and I have this already published. If you want to read, there is a full paper in my website and in archive. It's still in the pipe being reviewed. Okay, so this is I'm going to give you a theoretical result to help you to understand deep learning in a slightly different angle, and then I would, you know, just show you one example of how we use neural network in physical layer communication problems based on these theoretical understandings. All right, let me go start with the first part of this. Okay, so the first question is, what does neural network do? Well, what it does is obviously information processing. This is a common neural network of image processing with layer, convolution, some kind of pooling, and at the end, I get a whole bunch of nodes, activation, and then they can be used in classification. I like to abstract this away into a picture like this. This is my favorite picture of a neural network. So this is the input, whatever it is, and I have this red line here represent whatever the number of layers of whatever connection you have to, you know, of processing. And this, after all of these input processing, you get a layer that's right before the output layer. And this, again, I'm a lazy person. I just draw one node. You can have whatever number of nodes you want. But whatever it is, it's a function. It's an activation function of the input. We call this the processing result. This is your network, whatever complicated structure it has. It's processing the input into a S, and we call this a feature of the input. What sometimes people do not pay attention to is the weight in here. And from this node, the last layer node, to your class, suppose we're doing classification of K classes, and there are these links between this processing result S to the output different class. And you can think of that because each link has a different weight. You can think of this as weight as a function of which class it is. So this is what we call a corresponding feature, the output feature, V of Y. So what a network does is to process your data input into a feature of the input, and then with a matching feature of the output V of Y, and you know, put something out. And one could use different loss function in here. The one that we would like to think of is cross entropy loss with softmax output. So, you know, whatever the terminology means, you can imagine you try to use X to predict some class you're trying to match. You're trying to learn a model. So basically, you're trying to learn these features S of X that carries information that can be used to predict the value of Y. And the best way to do that is to approximate the true model between X and Y, the dependence between them. And so what features? Well, it just said informative features, right? So you can see that this entire learning and training complicated process is trying to select what's called informative features. Those feature functions that you can use to make predictions of the value of Y. And you know, we will say this kind of problems we have seen in classical signal processing, it's very clear what kind of informative feature we want. We want to do sufficient statistic, which is a feature of a function of the data that carries all the information that you need to make your inference work. Right? So this is the classical approach is sufficient statistic. You want to capture all the useful information. Now the problem changed a little bit in the context of neural network in big data, because your input data is often very high dimensional. And no matter how complicated your network that you want to build, it's just simply not possible to actually get a sufficient statistic. Meaning that we actually cannot take enoughly many functions to capture all the useful information. And in this case, what happened? You see the problem started to change, that now we have an issue to prioritize. Meaning that we have to talk about not all the information, but there are somewhat useful information, and depending on how somewhat useful, I need to decide, maybe some of them, this is not useful enough, then I would throw away some information. So this is lossy, and the lossy, the criterion you use to choose among these somewhat useful information pieces is it has to be based on a measure of how useful they are, quantitative measure. How relevant is this piece of information to the decision task I have at hand? I like to argue that this kind of question are intrinsically difficult in information theory. This happens because of our grandfather, right? Shannon himself. In his 1948 paper, this is a sentence he had in like the paragraph 2. He said the semantic aspects are irrelevant to the engineering problem. Semantic aspect meaning when I have a feature function, when I have a piece of information, what does it mean? What question does it answer? This is the semantic aspect. So what information does it carry? He said that they're irrelevant to my engineering problem. The engineering problem is communication problem, right? He said, well, to me, whatever information it carries, my job is to take it to the other end and reconstruct it perfectly, right? Whether this is a information about a image or this is a information about a 911 call, they're equally important for me. I'm going to take it to the other end of the communication channel and get it recovered, reconstructed. Right. So his engineering problem, communication problem, allowed this simplification so that he can ignore what is the meaning of information. But it happens to be that we're talking about a different engineering problem here. That in these neural nets with big data processing, we do care about the semantic aspects. So which makes some simplifying assumption made by Shannon no longer valid. Right? So we changed the problem already. This is a hard problem. Now to do that, this is our answer to this problem in general. This is the more theoretical part of this talk. I'm going to introduce a notion of information vector. Well, to start, it's actually not that hard. You can think of any variation of distribution as a vector. So I'm here drawing the space of distribution. Suppose you have some data that you know it comes from an ensemble of P naught, but you observe an empirical distribution of Q. So that's a change, right? So this move. And this difference between the two distributions are pretty obviously a vector in this rather high dimensional space. Right, so this is what we call information vector. And the classical information theory measures the distance between two different distributions or the length of this vector. And that measure is often done with KL divergence. And that measures the total amount of information. All the other metrics like entropy, mutual information are KL divergence, special cases of those. And I'm going to actually make some technical assumptions in this talk that these movements are very small so that I can have a local approximation, although I'm not going to show you exactly what kind of approximation I'm going to make because I'm not going to do any derivation, but I need to have a disclaimer that what I'm going to say are not generally true. They have to be based on this assumption. And we would like to write this in a vector form. Again, it's a pretty complicated form. I'm not going to do any derivation, so there's really no point for you to remember this specific form. But you know, it's just a difference between the two different distributions written in a vector form and make some scaling, right? With a very strange scaling, you know, the point that I show you this is to tell you there is a clear mathematical way to write out this in a vector form. Okay, well, there's the vector form you can write in many different ways, but we choose this particular way. Again, there's a reason that I'm not going to show you the derivation. I will show you the result, and those results can all be supported if you follow this particular definition. Now, the good idea of this information vector is that we can put not only the difference between distributions, but pretty much everything that else we want to talk about, all in terms of information vectors. For example, I mentioned a lot about a feature function. A feature function is a function that you would like to evaluate on your data to make decisions. And you know, if you want to evaluate on your data, you may as well take away all the mean or constant shift on these feature functions. So you can, without loss of generality, make them zero mean. And at this point, you can actually think about this under the local assumption. Every function you would ever want to evaluate can always be thought as a log likelihood ratio function between two different distributions. Every function is a log likelihood ratio function between two different distributions. And so what this does is we just define the information vector for the difference between two different distributions. Now, with this step, you can say every feature function I would possibly want to work with after I make them zero mean, after some local assumption, is a vector. I can write a vector form of a feature function. Similar thing happened to a query. Query in our you know, terminology means a decision that a inference task you would like to do. For example, a binary hypothesis testing problem is a query. It's a simple one. And if you think of what is a query, well, I'm trying to make a decision between two different distributions. Well, two different distributions have a difference, and I can write that as a information vector, right? So a simple binary hypothesis testing query can be written as a vector form again. And you can think of a parameter estimation along an exponential family, if you're familiar with that. That has an intrinsic relation with the binary hypothesis testing problem. And that can also be thought as a vector. You know, a more complicated classification, what happens if you have more than two hypotheses? Well, you just have a whole bunch of binary hypothesis problem that you need to do. So we call that a bundle of binary decisions. And again, it can be written as a bundle of vectors, right? So that's the idea is that with this information vector notation, we actually can write all of these things, functional space of distribution, and we can put them all in one picture. And by doing that, what do we have? So this is the three conceptual picture. This is what we observe, the data. We observe its empirical distribution. And this is what we want to design a feature function to process it. And this is what we want to do, a classification tasks. And they're all written in this information vector form. Now, when you have a vector, there is a norm of this vector, and each of the norm has some meaning. We mentioned the norm of observation of an empirical distribution. That's you change from P naught to Q. That reflects, that's actually a measure of the total amount of observed information in the classical sense, in the KL divergence sense. And the distance between two different distributions in a binary hypothesis testing, for example, that's the the norm of the vector to specify this inference task. It's usually telling you what is the best possible performance in terms of error exponent, in terms of pretty much every other measure you could have. So this is the best performance you could have, or how much the problem allow you to operate. Now, these are what the classical information measures, entropy, divergence, can measure. Now that's measuring the length of the information vectors. What we're going to say is now, because we measure information in this vector form, we can actually capture more meaning of that. So let's think of the inner product, or the inner product between the observed empirical distribution and a feature function. That's what I can draw this picture here. Suppose this is your P naught, your ensemble, and you observe some data that has an empirical distribution of P hat, and we can write a vector form of that. And now, suppose I would like to process this this data, this P hat data, whatever sequence has this empirical distribution, by calculating a feature function on this data, and I will calculate the empirical average of this feature function. And this is the feature function. As we mentioned, feature function can also be written as an information vector. Let's write this as this new guy. It turns out with that slightly interesting notation of information vector, this empirical average happens to be precisely the projection of this information vector P hat onto the direction of F. Right, so this gives you a rather insightful statement. It says that now this is my total information I observe. When I find a feature of that, when I evaluate a feature function of that, what I'm doing is I'm taking a part of this total information, and which part, that's a projection in this information geometric space. Right? I'm taking one subspace of this thing. Now let's look at the inner product between these two. In the product between the feature function and a particular classification task. Now, I have a similar picture. Let's look at this blue arrow. These are two different hypotheses. Let's say P of x given u equal to 0, P of x given u equal to 1. They live on a difference, and I would write that as a vector form phi. And if you think about it, if I observe some data outside an empirical distribution anywhere on the space, how do I do this binary hypothesis testing? I should evaluate the log likelihood ratio function between these two different distributions, which corresponds to project whatever I observed into this blue vector. And that's taking the part of the information useful for this binary hypothesis testing problem. Right, so that I didn't even draw, but that's a familiar picture that we have. This look like a Gaussian, but it actually applies to whatever general hypothesis testing problem, right? So you can just project and then take the sufficient statistic on this blue line. Now, I like to think of this in a slightly different way. That now suppose what happens is we didn't do that. We didn't find the sufficient statistic. Instead, we choose a different feature function in this orange direction called the phi prime. Suppose I choose a feature function that's not quite the sufficient statistic of this problem. Then what happens? Then what happens is I would project everything onto this orange line. Then the distance between these two hypotheses get into this projected way gets shorter. Right, so that's basically saying if I use the wrong feature, not the sufficient statistic, then I lose my performance by some amount. And how much do I lose? I lose by obviously the angle between these two different vectors. So the mismatch between the chosen feature function and the feature function your classification task wants measures in a sense, measures relevance, measures how bad it is, right? Or how good it is. So if you calculate this in the product, it answers you how relevant is the information in this orange direction to the question in this blue direction. Right, so we want to make that as large as possible. Now, so this gives you the basis of that lossy feature selection idea. The key thing you should see is that because we measure information in this vector form, it has not only the norm, but also the direction. And those direction actually can tell you how relevant or what is the contents of this information, with respect to the questions you want to answer, right? So a general classification problem usually it's not a binary, it's a collection of queries. We basically can write all of those queries into a matrix form, right? So each conditional distribution is written in the matrix form. Again, I'm flashing this to you on what it looked like. There is a thing called the canonical dependence matrix. You can just think of this as a bunch of binary hypothesis testing vectors, stack them together into a matrix. Yeah, and if we have a lossy choice, meaning if we have a limit of how many features we can take, what is the problem is we are going to choose some features of X so that these features have the predictive power to the value of Y, right? Now, if you think back to what we just draw in that relevance, with the idea is basically you want to say how these vectors vary with Y, the vectors in terms of distribution of X. How do they vary based on the value of Y? You want to capture them with a certain direction of projection. You want to find the direction that after you project this variation to, it captures as much energy as possible. Now, let me rephrase that. You have this B as a matrix, and all of its column vectors are different to each other in this way and that way, and you want to find a subspace to project it so that you capture most of these difference. Yeah, and how this should remind you one problem that we like the most, the so-called singular value decomposition problem, SVD problem. Yeah. Okay. And how do I get rid of this? Okay, now one more. So here's a claim that's kind of surprising. We claim that neural network is the SVD solver. It solved the SVD of that B matrix. So again, this is my neural network. I remind you the notation: S as the processing feature, V is the output feature. And we claim there is a B matrix corresponding to the input-output data has a joint distribution. And you can write that, and you can write it as a B matrix. You can write a SVD. It has phi I and psi I as the singular vectors. Sigma I is the singular value ordered in the descending order. Sigma 1 is the largest. Let's write this thing out, right? And the claim is that if you run this neural network, it's going to choose feature functions, this Sx, correspond to phi 1 to phi k, the first k singular vectors on the X, and in a descending order. And there is a set of corresponding output vectors on these weights. It's going to look like the other collection of singular vectors. Right. So you can actually run this. This is surprising. You could run this, and I have a little Wikipedia page on my homepage, and you can find a link in there. There I have the code and the explanation of every step on this. And the bottom line is you're going to see some picture like this. So the idea is I would generate data myself with some joint distribution of PXY, and I put that X as input, Y as the label, and I run a neural network and check what the neural network generate in these feature function and weights, and I plot it against the theoretical calculation of the B matrix, and this is what it looked like. It matched really well. And now there is a whole bunch of questions you would like to ask at this point. How did the neural network solve SVD? Turns out, if you think harder enough in that backpropagation procedure, to each time you get a loss function, you propagate the derivative back. That backpropagation procedure can be written as equivalent to a power iteration in solving SVD, right? So that's the thing. So that's a little discussion of that. Now, what did we learn from this? I'm not claiming that big inception thing you can do, that image processing network you can do with a SVD. But here are a few things I hope I managed to deliver. Number one, important, is we use information vector to measure relevance of information. And this is an important new information metric that's used in these kind of problem. And two is neural networks select feature functions based on this. In realistic neural networks, it's a little harder because networks has many layers and it has limited representation power. You could always think of that as an approximation to these ideas. Now, the most important take-home message I have on this is now if you understand what neural network is doing, trying to get this informative measure feature functions according to this metric, then you can be brave in editing those features. Editing those features to do what? To incorporate prior knowledge, side information, structural constraint, whatever you have, you want to put into your problem. And a commonly used approach of editing, of putting some influence to neural network is by designing a regulator, change the loss function, pooling, change network structure. But if you think of whatever is happening in those neural networks, just getting a feature function that carries some information, then you can take it out. You can pull it out to make it look like just one function you designed by yourself. And this is the idea. And then you can use it in your whatever classical design, right? So this is what I call the hybrid design between neural network and the conventional processing. So the hope is to run one example that everybody knows, and let's talk about how actually we can do this. Well, we would use a neural network in communication problems. In what kind of problem? That's the first question. Well, I would say we need to let neural network have its advantage. Meaning where you use them is usually where you don't have a clear model, or the clear model is too complicated. You can't find the optimal solution based on that. And this corresponds to the non-Gaussian case, non-linear case, non-stationary case. That's where we really want to do. And should we use in physical layer or higher layer? I would say higher layer give you more potential because we know it has less clear model and more activities you can play with. But I choose to do a physical layer problem in this talk, well, mainly to illustrate the idea. And also you could imagine when we talk about this hybrid design, combining neural nets and conventional approach, in the physical layer where you have relatively better model, you can expect this hybrid design is very close to what we know as the conventional approach. There's, the element of neural nets should be smaller. Right. So let's see, that's going to be something that's close to our heart, and with a little twist on neural nets. Let's see how do we do that. That's the idea. And the key challenge in here is we want to design a system that I can change parameter to it, right? So we can use in all different scenarios. Okay, so the problem we're going to talk about is this symbol detection over interference channel. This is, you can think of this as a Y vector multiple antenna receiver with a single transmit antenna X. This is fitting coefficient H, plus some noise and interference also that. Okay, so this is a familiar setup, and we would think X as either QAM, PAM. I'm only going to make plot on PAM because it's easier to plot. I'm going to assume CSIR, meaning H, this entire vector is known as the receiver, and the ugly part is I'm going to assume W to be non-Gaussian, and we're going to assume it's fixed with a fixed and PDF, but not known to anybody. And of course, later on, we can allow it to change and see how much we track this PDF. This usually comes from your neighbors sending interfering signals, which is also PAM modulated, for example. And so you get a rather non-Gaussian effect. And standard approach of handling this is what? How do we handle non-Gaussian noise? Mostly, we don't, right? Mostly we just pretend the thing is Gaussian. Let's measure its covariance and then use a linear MMSE plus tool to estimate the value of X as a real value and then do a minimum distance to make a decision. We'll see how bad it is in some examples. And there's actually a ton of analysis on why that is missing some of the performance, right? So now the question is, can we do that with neural network? Can we use neural network to learn this non-Gaussianness? That should be not too difficult because after all, it's a low dimensional business, right? How many receive antenna can you have? It's not very difficult to learn this PDF, but the question is, how do we use all the structural knowledge I have? For example, I know H, I know this is QAM, I know this is additive noise independent of this, right? How do we use that? And plus, if we train this with one particular H at one SNR, how can I use that corresponding in the solution for different SNR and different fading? One way we see a lot of practice nowadays is I would do a mixed training. I would change this H and SNR and put a lot of sample to train a bigger network. Hope the network can handle it. A rather robust network that can handle this as input. That's definitely not the efficient way of doing this. Yeah. Let's see how do we go proceed in doing that. To start, let's start with the first simple idea, is that let me recognize that this X is PAM, so it is very regular, meaning it takes value from -3, -1, +1, +3. Right? The distance is always the same. Plus, I do know this H. What that is if I write this conditional distribution of Y given X equal to +1, there is a shift invariant or repetition over amplitude property. It's the same as the density of Y plus 2H if your X is +3, right? So if you transmit 2 more H, and that's the same way. With this observation, we can say that suppose I have made a decision. This is a neural network with Y coming in, and whatever neural net, it's not very big. It generates these processing. This is a 2-class softmax, and it generates this log likelihood ratio between Y given plus or -1. Yeah. Suppose I can get this. Then, because of this repetition, I can do the same thing. I would say, let's Y equal to the input, let me put a Y plus 2H, and I run exactly the same network. What that's going to come up is this different log likelihood ratio, the ratio between X equal to +3 and +1. Similarly, if I put a Y minus 2H in, I'm going to get this log likelihood ratio. And suppose I have all 3 set up. What I can do is I can accumulate these by generate 0 is equal to this, and one of them give you this log likelihood ratio. Sum up two of them, give you another one. Sum up all three, give you this guy. So what you see is now from the input as y, I made 3 copies, sending exactly 3 identical copy of neural networks, each one handling a binary decision. And the output, I did a little bit of accumulating, and I got all 4 likelihood come out. Right? So you can think of this as a general input-output model that take y in and this quaternary likelihood ratio coming out, but I'm reusing this binary decision module. And the reason I can do that is I use the fact that this is a regular distance and this h I already know. And you can think of this as I'm restricting whatever is generated over this big model to have this repetitive structure as we have described in this problem. Right? So this particular connection to reflect the knowledge of the structure of the problem. And you know, people call this CNN over amplitude or whatever it is. And the interesting thing is when you train this network, you can also reuse your sample. If you receive a y that's actually based on x equal to -1, you can shift it, right? You can put a y plus 2h in, get another sample in this. So this kind of a repeat the binary module idea multiplies your number of samples and also make the training much faster. Yeah. So now let's go to think of now we can focus on this binary decision module, and this is the important part of the talk. How do I actually train this? In particular, suppose I train this under a one feeding coefficient HS. How do I use it in HT? This is in the transfer learning terminology. This is the source problem, and this is the target problem. Right? And so what's transferable? What knowledge do you have to transfer? Well, we like to learn the PDF of W. That's the only thing that's transferable. That's the only thing that's you can transfer between this problem and this problem. And the question is, if I train this network, apparently it has learned something about that PDF of W. Where is it, right? How is it stored? How do I use it in the next problem, right? Now I'm gonna do a concrete example where I assume this W comes from some PAM of other interference users, but my receiver doesn't know that. So this is the picture. Yeah, this is the thing I would like to design. And this is the, I have a 2-dimensional Y space. This is HS. One corresponds to 1, the other is -1. I have some interference. I have 2 interferer and the standing PAM also. So I got these blue dots without noise. It looked like this. And you can see this is a pretty bad situation that my interference noise is non-Gaussian. And a classical approach is I will pretend this to be Gaussian and calculate the covariance matrix between these 2 clouds and make a linear decision between the 2, right? And you see the linear decision has some problem. The blue one has this red dot and this red dot in it. So that's meaning without any noise, I'm making a 2 out of 16 mistake. This is kind of a strong interference situation. Now, what we really want to learn is this guy, is the PDF of W. And because I use this simple model, I can explicitly write out what is the optimal decision region. It looks like this. It's basically the minimum distance, the bisector between every pair of neighboring points. Okay, so it looks like this. And to generate this, what you need to learn is the PDF of that interference or the log likelihood ratio. In this way, it has these piecewise linear shaped this. Yeah, so the question is, can we let the network learn this? Turns out this is not that hard. You can it's not too bad, right? So this is you can generate the data and its label and just send it into a neural net. It doesn't take a very big network to learn something about this. And this is what I would do. I would generate some data with a little bit of noise, not too much noise, and send into a neural net. It's probably 2 or 3 layer, very small neural net, and let's let it learn. And this is what it learns, right? This, I'm plotting the contour of red versus blue, right? So this is log likelihood ratio. And you can see this doesn't, and this is the 3D plot of that. It doesn't give you much. The problem of this is it doesn't do too well, particularly on these edges, on this extra edge, that in this part, your neural net all decide as blue. In this part, your neural net all decide as red. If you think about it, why that happens is because, well, these are all my samples, so I don't see any sample in the middle. So my neural net can basically do anything in the middle and still do pretty well, because there's no sample in here. You can arbitrarily make decision in here, so you just take whatever is convenient to him. So in other words, a lot of training problems we have in communication, the neural net doesn't work too hard because there are a lot of space that it can arbitrarily make decision. So in order to avoid that, we did a approach to force the neural nets to work a little harder to generate data like this. So we call this throwing some sand. You can still see the cloud of modulations in there barely, but what you do is you put a lot of randomly thrown dots in the space and randomly label them half-half, right? So what this does is in the middle, in these areas, there is some extra points that's both half-half being plus or minus. So this tells the neural nets, don't make decision here. In here, in the middle, you should keep your likelihood ratio to be 0. Right. So the actual data we put in the sand is a lot more. If you have plot that, you can't see, right? And this is what, if you train the net, it has this really strange shape. In 3D, it looks like this. It has some peak. It has some bottom negative peak. But when you look at this, you see, hey, actually, this is not too bad, because wherever I have a blue, well, it is actually quite high. Wherever I have a red, it is opposite. Yeah, it's pretty good in this area, but outside it's not. Meaning what? Meaning that the network actually learned something in here, but not too much outside. Yeah, outside is basically whatever is convenient. Well, which is not surprising, because outside you don't need neural network to make a decision. So we will, overlap this with the ideal decision region. You look at it, it's actually quite decent. Yeah. It's the neural nets, after all of these effort, only learned to make a right decision in a region. This region you can define as basically the overlapping region, basically where you need some nonlinear, non-Gaussian processing with it. So this is really the region that's difficult to make decision with classical approach. This is what we call the knowledge region that neural net actually learn. Let me put this in a picture. So this is the noise, the interference and noise. If you want the PDF I like to learn, and this big oval is my covariance structure, right? So what we're arguing is, turns out the neural net only learned this overlapping shaded area. Outside, didn't quite learn anything. Well, that's okay. Now this is my decision procedure. I would say let Y come in, and let me first make a decision. Is the Y in this area of interest or not? If it's not, let's go to linear decision making, which is perfect. Yeah, so that's what we do before. And only if Y is in this area, let me use that to train or to run through this small neural net and make a decision based on that. So this, I'm separating what can be made, where the decision can be made with the linear approach, and those that you have to make with neural nets. And after you train and process the symbol in this, what you have done is you have learned a part of that PDF of interference. Which part? Well, it's basically this part. You learn the PDF in this area, which corresponds to this area. And if you take the negative, the red part, you also learn this area. So in some sense, you could say, well, we failed in some sense of our task. We went out to say, can I design a neural net to learn that PDF of the interference of W? Turns out we didn't. We only learned that partially. We only learned the PDF in some areas. That turns out to be already quite useful. So this is how we use it in reality. So suppose you train this for a source problem, which HS, and now you need to use it on a target problem with HT, which you also know. And what you know is this W has the same PDF. And the question is, what you learned in here, can you use it in this problem? Well, what you learned is here. This is the source problem. You learned the PDF of W in this intersecting area. But now what you want to do is you got a new problem. You can again do that linear processing. You say anything out of this intersecting area, I would do linear processing, but I really would like to know the interference PDF in this purple area. Yeah. How do we do that? Well, at least some part of this I have learned. Well, I have learned this part from the previous problem. I have also learned this part from the previous problem, from this red part, right? So I'm obviously showing you a rather extreme case where these two overlap is good enough to capture a lot. Well, in reality, it captures some, right? So that part, that is the part you can use your neural net. Other part, well, you didn't learn, can't use, right? So that's the idea of reusing the knowledge you have learned before. So this translates into a receiver structure like the following. This is my incoming Y vector. I'm hoping to, again, doing the binary module, I'm trying to generate this log likelihood ratio between plus and minus HT. This is the target problem. Well, I'll do the first thing. I'll say, let's decide, do we need nonlinear processing? Can I use the linear, is it in that shaded area, right? If it's not in the shaded area, I don't need nonlinear. Let's do linear decision, end of story. So that's a pretty good decision to be made. And if I do need that, meaning it is in that, intersected part, I would do two shifts. I will shift this by HT and minus HT. And then I'll ask question, have I learned this noise realization before or not? By checking the problems that I have learned before, the source problem. If I've learned it, well, nice. I'm going to use the corresponding neural nets to generate the likelihood ratio. If not, let's fall back to the linear decision, right? Or in this fallback linear decision, and in this fallback part, I could say, let's do some little bit more training over here. In reality, what we can do is we can say, well, this one source problem may not be enough. Let's learn a few of those. Let's learn a few of those. Then in this decision, I would say, well, was it in any of the previously learned situation? And if so, let's take out that corresponding neural net and use that.
Lizhong, probably we can speed up a little bit.
This is my last slide.
Oh, okay, great. Yeah.
This is my last slide.
Yeah.
So this is sorry, I really can't see all the questions, but this is the structure. Now, concluding, I'm not gonna show you what kind of performance I get out of this thing. You can see I only improve over the linear processing because I'm making that decision on do I need nonlinear or not, right? So this is I can create a good performance by this approach. And I also want to emphasize this is only one example of applying neural nets in a rather physical layer problem. And the important thing is we like to incorporate domain knowledge in deep learning. And the way to do that is what I call a hybrid design, so that we can focus on the learning power only in that, you see, on that intersecting area where, you know, things are non-Gaussian. Let's just learn that. And all of these are based on the concept of information vector, which we can explicitly answer, you know, what is this information, right? What is it useful for, right? So this is a sort of the theoretical background on this whole thing. And I'd like to state that with such a general approach, we should expect a spectrum of using hybrid designs to mix rather analytical method with neural nets. You see in my design, in that receiver structured neural nets, it's only a very small component because the problem is, you know, almost I can solve it analytically. So we have, you know, a rather analytical solution with a tiny component of neural nets just for the part it's needed. Yeah, so that's all. How do I see that?
Okay, thank you, Lizhong, for the informative talk. Now we can have a Q&A session for a few minutes. Sorry for a little bit delayed, but we do want to accommodate a few questions. If you have questions, raise your hand if you are attendees, or just unmute yourself. You are in the panelists.
Sure. Okay. Thank you for your great lecture, Professor. I have a quick question about the slide that you mentioned. We can find SVD using the neural network. Can you bring that slide? Okay. I have some question from that slide.
Here.
Yeah, I have two quick questions here. The first one is the last line. You mentioned that backpropagation is equivalent to the power iteration. Could you explain more how? Yeah,
so so what it does is backpropagation is I will fix this part. I basically fix one of the feature, yeah, and optimize the other one. Yes.
Yeah.
And then I will fix these, optimize the S, right? So I'll fix one, optimize the other one, and fix the other one, optimize this one. Yes.
Yeah.
So that can actually be written as a conditional expectation, or you actually could write that as I would choose my Sx as E matrix multiplied by Vy. Then I would choose my Vy as B transpose multiply Sx. So that's a proof you have to do. I didn't do that, but you have to actually read that thing.
Yeah, that means you have some reference for that, or one of your is a special paper of yours.
Yeah, it is. It's in our full paper of the thing. It's you can find on my website archive, and you can read the Wikipedia page.
Okay, great. And another question is that you mentioned the output weight is chi. It seems to be correspond to the right singular vectors.
Yes.
How we can the left and this singular values, because we can see that the output is the singular values, or
right.
the singular values.
These are all singular vectors. Singular values come out. Singular value is a way to measure how close are. So you can think of this the dependence between x and y is decomposed in these singular modes.
Yeah.
And the singular value tells you how strong is the coupling on each mode.
Yeah.
So if your singular value is large, that means your decision would be good.
Yeah, you are right. But where is the singular value? Is the weight? Is the output?
No, it's not. It actually shows up in the performance, because in neural nets, these vectors, these functions are all normalized. So you can't there's the singular value basically tells you how good is your performance. Yeah.
Yeah, that means if one of the reasons that we are doing SVD, we want to find singular values. Now we suppose the network trained now that now we wanted to get singular values. How we can get it?
But yeah, then you have to see the performance. Right. So if you use neural network, it only find you singular vectors, and actually find you the linear combination of singular vectors, and then the performance shows you the.
Oh, okay, got it.
Mm-hmm.
Thank you
okay,
very
let's
much.
move on to the next.
Yes.
We don't have time to talk this to details.
Yeah.
I have one question. Can I ask?
Yeah.
So neural network approaches have been very successful in speech recognition in such fields where the error probabilities are relatively high. I mean, there was a lot of celebration when they went from 80% correct to 95% correct,
Yeah.
right? But in communication problems, we typically worry about error probabilities that are like 10 to the minus 3 or much smaller.
Yeah.
And so you would think that the complexity of training, that means the number of training samples you need, would become prohibitively large, right? So I was wondering if you had some comments about that in sort of a general sense.
It is actually this is a very good question. Remember in this part that I had the similar issue, right? So if I train on a rather high SNR thing, and it's a pretty high reliability correctness, and then what happens is the neural network just do something random in the middle because they never see this challenging cases.
Right.
Right. So what we did is we say, well, let me give you the challenging cases. Right. So when we train the network, we put in some sand to say, let me put these man-made samples in the middle to screw it up, so that forced the neural nets to do something in these difficult cases. Well, this can be done in some cases, but maybe not all cases. Right. So this is a case-by-case operation.
So it really helps to have a lot of domain knowledge over here.
Absolutely.
When you're doing this,
yeah, you need to know where you put the set, right? Very good.
Yeah, you chose a beautiful example, I have to say. Very, very intuitive. And yeah, thank you.
So I'm a little over time, so let me stop sharing, right?